That happens. Sometimes you spend a couple of hours trying to solve something and then realize it was already given to you because the instruction already said it. Happens to me all the time. So, um, okay, so the basically with this particular slide, all I wanted to is like sort of bring up some points. I get asked a lot about programming languages. So, like for example, with my students, when we have projects, usually there is um, there are many ways to solve a problem in many different programming languages, and of course they all have their pros and cons. So some programming languages compile into faster code, some are more suitable for large software projects, some are not as fast, but they are easy to type. In particular, if it's a small, quick and dirty program that is just intended to answer a question. It's not a software that you want to use for other people to use, but it's really writing programs to solve your particular immediate problem. So there's a variety of programming languages, and I actually tried to not to be just to be limited to one. I try to keep current on a number of languages that I use, and often, rather than trying to put everything into one program, I actually might write different pieces of code in different languages and just tie them together so that the data, whatever one program produces, is then moved to the next program and it just processes. And sometimes that helps to get quick results, because certain things might be easier in one language than they are in another language. And part of this, these kind of decisions are basically came in here. One of the things that is really critical for this particular simulation, for this particular problem, is that I can create a map or this grid where my dude runs and my rocks are stored. That's fairly static, so it doesn't change and I only need, for one run, I only need one representation of that. Other problems, like I looked at the problem that was the protein folding, we actually have to create, for the protein folding, you would have to create multiple alternatives, and that relates back to dynamic memory management. And dynamic memory management in C is possible, but it's a little bit of a headache. So other languages like Python or even Java, who do garbage collection and do something like this in a sort of more built-in, interesting way, might be more suitable for that. In particular, scripting languages like Python, where you can create lists and you can add things at the end of the list without having overcomplicated container classes to use. So that would make that's also a factor that I would use to make the decision which programming language I use. So I wanted, for this particular program, I wanted to keep it very simple, and so this program is actually written in C, and it's plain C. Input, output are something I want to get rid of, I want to make really easy. Since I only have a handful of parameters that I sort of consider input, and I could actually add the starting position, I decided to not even put them in my program as like reading in these values, but rather define macros in C and then set these at compile time. So every time I run a simulation, I actually compile the program first. Since the program is just very short, it just takes a second. So I basically put it in my, I compile the program with the parameters I want, and then run the program. And my output is also, it doesn't have any text, it's just numbers. And of course, that only works personally for me because, I mean, because there's no explanation what these numbers are. But if you're writing a program and the program is just to solve your problem, then you basically know what you're doing. This is not for everybody else, so you don't have to spend a lot of time explaining or having some type of user interaction in there. I did a little bit though, because one of the things is, of course, within a few hours I will forget what I actually did. So if I finished this yesterday and I want to come back today, I need to know kind of something to remind me what I did. So here are some tools that so basically this is going to be is completely written in C. So I'm going to show you the program in a while and then go through some steps. Again, keep everything very simple. Sometimes also what helps is, and a lot of people might not be too familiar with that, but it's definitely worth it to look at Unix and look at a Unix command. So you see here so let's say, for example, I write a program sim that produces these numbers. So let's say my simulation program runs a simulation, and the output is really the number of days it took the dude to basically finish the task. And given this is random, we expect there is of course, every time I run it, I might get a different number. So if I run it 1,000,000 times, I would get 1,000,000 different days, and then what I might be interested in is a distribution. How many times out of these millions did it take 58 days? So let's say my simulation program actually runs the simulation and just prints out the iteration number and the value. I did that in the printf. If you're somewhat familiar with C, so I would print out, let's say, the number of iteration, the iteration run, and the number of days. That would be my value in 2 columns. The little program cut in on Unix and Linux, I can actually take a file that's basically it's rows of numbers and say I just want to have the second column, or I want to have just the third and the fifth. So this cut allows me to cut out certain columns. Then my output now basically would produce just 1 column. Then I can sort it. The unique command actually takes duplicate out, or unique with the option -C can also basically produces a number. How often did this value actually appear? Then the org command is actually not really necessary here. I just use that to actually switch my columns around, and then I direct everything into a data file. So what I actually created here is this line of Unix commands, and you see the vertical part is the pipe. So I start out simulation program, run through all these programs that already exist, and at the end what I have is actually a file that has a histogram. It has the values, the number of days, and how often these days appeared in my million or whatever simulation runs. That's a lot. And I saw, is there a question? Or just a gasp? What is that? So I see, got it. Okay, so I brought this out here just to say refresh your Unix commands. These tools can be very helpful and allows you, once you get from, they're kind of cumbersome because all of them have different options and stuff. But when you get a little bit comfortable, when you get comfortable with them, you can accomplish a lot of things very quickly. The other thing that of course, one of my favorites is GNU-plot. If you haven't looked at GNU-plot, it's usually, because it's fairly lightweight, it's usually available on every Linux system. But of course, you can also install it on your Mac, and I believe there's a Windows version. A quick program that can create fairly sophisticated plots, but it's also you can very quickly produce a plot, and it's fairly lightweight. So the command here, plot, actually to see this. Of course, what you see here, this picture is not what that is. I just took a random picture. But let's say I would produce that histogram, then all I would have to say in GNU-plot would basically plot hist dot, just the file. The rest is actually not necessary, but you can change options in there. Okay, so these are these are basically just some thoughts to say, okay, how do I go about it? How do I write my program? Now, when it comes to implementation, of course, the first thing I need to consider is the movement of the drunken dude. Then I need to make sure that I understand the programming logic so that the rocks are moved in a proper way. I need to implement that, and also, of course, test for the terminal condition. And then I need to be considering my input and my output. I already mentioned that, and I think it becomes clear if you're not familiar with C when I show you the program to basically create the how I just basically set macros and then define at compile time what these values are. And then also for the simulation to results, I actually just used standard output. So I just use printf, it comes on the screen, but then I can redirect it on the Unix. I make use of that to redirect it into a file, or even if I want to process something else. So that way I don't have to do any file management, I don't have to open files, and basically every time my program just produces a sequence of numbers. And that's about it. It sometimes might not be possible to do it just as slim, because you might have different results. But then again, there are also ways to put everything in one file and then use commands like grep to just extract the information that you want for a particular way, rather than trying to create a more complicated way in terms of opening files and writing files. The reason why opening a file is even though it's fairly it's very simple, but imagine you run your program. So let's say you run a program and I just call it output.dat, and it produces a file output.dat. But now let's say I want to run multiple instances of my program in the same directory, and they all call them output.dat, then I get a conflict. So if I need to make sure that my programs might run, let's say for example, I might run multiple processes on different nodes, but they share the file system, then I would have to make sure that each of them has a unique file name, and it just adds another complexity to it. So sometimes it's easier to avoid that. Yes. Okay. I appreciate it. Sorry.